Welcome to today's paper reading. Today's paper is titled, THOUGHTSCULPT, Reasoning with Intermediate Revision and Search. This paper, titled THOUGHTSCULPT, Reasoning with Intermediate Revision and Search, was authored by Yizhou, Kevin Yang, and Dan Klein from UC Berkeley. It is currently under review as a preprint. The paper introduces THOUGHTSCULPT, a method designed for general reasoning and search tasks where outputs can be decomposed into components. This method employs Monte Carlo Tree Search, MCTS, to explore potential solutions, constructing them incrementally and evaluating them using domain-specific heuristics, often facilitated by a large language model, LLM. A key feature of THOUGHTSCULPT is its action space, which includes revision actions allowing the method to revise parts of its previous output rather than solely continuing to build new parts. Empirical evaluations show that THOUGHTSCULPT significantly outperforms current state-of-the-art methods across 3 challenging tasks. It improves story outline interestingness by up to 30%, increases word success rate in Mini-Crosswords Solving by up to 16%, and enhances concept coverage in constrained generation tasks by up to 10%. The performance of large language models, LLMs, is significantly influenced by distinct prompting strategies. For instance, chain of thought (COT) prompts LLMs to produce outputs through intermediate reasoning steps, enhancing problem solving without model updates. Self-consistency with COT, COTSC, further improves consistency by generating multiple COTs. THOUGHTSCULPT is a novel graph-based framework that allows LLMs to build an interwoven network of thoughts, featuring a self-revision mechanism and incorporating Monte Carlo Tree Search, MCTS, to navigate the vast search space. Experiments across tasks like story outline improvement, mini-crosswords solving, and constrained generation show up to 30% improvement in interestingness, 16% increase in word success rate, and 10% improvement in concept coverage. The code will be open-sourced upon publication. In the realm of feedback-guided generation, human feedback has been shown to enhance large language models, LLMs. However, due to the cost and difficulty of incorporating human feedback into automated processes, heuristic functions are often used as substitutes. Additionally, mechanisms have been introduced for LLMs to generate self-reflective feedback to improve their outputs. Moving on to graph reasoning. Approaches like tree search procedures enable broader exploration during problem solving, while a graph-based paradigm allows for more flexible modification of intermediate nodes. Lastly, in the context of language model planning, high-level planning is crucial for long-form generation and complex problem solving, often involving natural language outliners and structured schemas. LLMs are also utilized for tackling complex tasks with planning, such as in video games and code optimization. Figure 1 illustrates the THOUGHTSCULPT process using Monte Carlo Tree Search, MCTS. Each circle in the diagram represents a thought node generated by large language models, LLMs. The process begins with the selection phase, where a thought node X is chosen based on a selection algorithm such as UCB1, ECN4. In the expansion phase, a new set of child nodes X is generated using the initial instruction, the current node, and self-evaluated textual feedback. The expansion phase is detailed with the use of the thought evaluator and thought generator, which assess and refine the current solution. The simulation phase involves randomly selecting a node X from the set X, which then generates further nodes in a sequence corresponding to the decision simulator. Finally, in the backpropagation phase, the numerical feedback evaluated at the last node is propagated back to the root node, updating the scores of the nodes along the path. In this method, each formal output of the language models, LLMs, is treated as a thought node, denoted as X is an element of X0, X1, 11, where X0 is the root node representing the initial output given the task instruction I. The method is structured around 3 main modules: the thought evaluator, the thought generator, and the decision simulator. The thought evaluator assesses each thought node and provides feedback for potential improvements, which includes both numerical and textual feedback. There are 2 types of textual feedback strategies: holistic evaluation, which analyzes the entire thought node, and itemized evaluation, which assesses each subunit individually. This feedback is crucial for guiding the generation of new thought nodes and for simulating decisions to optimize the output. In this section, the authors evaluate their method on 3 distinct tasks: story outline improvement, mini-crossword solving, and constraint generation. They compare their approach against several baseline methods, including chain of thought, COT, self-refine, and tree of thoughts, THOUGHT, with depth-first search, DFS. The experiments utilized GPT 3.5 and GPT 4 as the base language models. A notable finding is that THOUGHTSCULPT, particularly with Monte Carlo Tree Search, MCTS, consistently outperforms the baselines across all tasks. This is evident in the continuous improvement observed in the story outline task, where THOUGHTSCULPT with MCTS shows a higher rate of interestingness compared to other methods. Additionally, the study highlights the effectiveness of THOUGHTSCULPT even when using DFS, demonstrating its ability to generalize to different search algorithms. Figure 2 illustrates the process of improving story outlines in our task. The thought evaluator performs detailed evaluations on the current outline, providing feedback on its interestingness. Based on this feedback, the thought generator proposes a set of improved story outlines. For THOUGHTSCULPT and THOUGHT, each node generates up to 3 candidate child outlines, aiming to enhance the interestingness of the story outline. Table 1 presents the average interestingness of story outlines generated by various methods. The initial outline, which serves as the baseline, has an interestingness score of 12%. The THOUGHTSCULPT method with Monte Carlo Tree Search, MCTS, significantly outperforms other methods, achieving an interestingness percentage of 89.9% with GPT 3.5 and 65% with GPT 4. This table highlights the effectiveness of THOUGHTSCULPT in enhancing the interestingness of story outlines compared to other baselines. Figure 3 showcases the average outline interestingness at each step, highlighting that THOUGHTSCULPT's interestingness increases more significantly with each step compared to baseline methods. This figure demonstrates the consistent pattern of improvement exhibited by THOUGHTSCULPT when paired with MCTS, contrasting with the lack of continuous improvement seen in methods like THOUGHT and self-refine. Figure 4 illustrates a step in the deliberation process for the mini-crosswords task. Here, the current crossword board is evaluated using a thought evaluator, and a set of candidate words is proposed for task 4.2. Each step in this process is equivalent to one rollout, emphasizing the iterative nature of the solution-finding process. Table 2 presents the results of the mini-crossword task for THOUGHTSCULPT and baseline methods, showing the success percentages of letters, words, and games. The data indicates that THOUGHTSCULPT with MCTS achieves the highest letter success rate when using GPT 3.5 and the highest word and game success rates with GPT 4. Notably, despite limited search steps, THOUGHTSCULPT, MCTS, performs comparably to the best results, while THOUGHT with GPT 4 underperforms compared to self-refine. This suggests the importance of a self-revision mechanism in this task. Table 3 presents the results of constraint generation tasks, showing the percentage coverage of concepts by different methods. THOUGHTSCULPT significantly outperforms all other baselines when using either GPT 3.5 or GPT 4 as the base language model. Specifically, THOUGHTSCULPT with DFS achieves the highest coverage of 79.6% with GPT 3.5 and 99.1% with GPT 4. THOUGHTSCULPT with MCTS also demonstrates strong performance, with coverage of 77.9% using GPT 3.5 and 99% using GPT 4. These results highlight the effectiveness of THOUGHTSCULPT in integrating and covering a high number of concepts in constraint generation tasks. Figure 5 illustrates GPT 4's preference for the final outputs in constraint generation tasks, focusing on both concept coverage and appropriateness. The figure shows that THOUGHTSCULPT with MCTS is significantly favored over THOUGHTSCULPT with DFS and a third baseline. This preference indicates that while concept coverage is important, the appropriateness of how concepts are integrated into sentences is also crucial. The wide margin of preference underscores the effectiveness of MCTS in generating outputs that not only cover required concepts but also do so in a contextually appropriate manner. The THOUGHTSCULPT framework is designed to empower large language models, LLMs, to handle complex tasks that require continuous refinement and deep reasoning capabilities. Importantly, this is achieved without necessitating any modifications to the underlying model architecture. By harnessing the Monte Carlo Tree Search (MCTS) algorithm, ThoughtSculpt enables LLMs to effectively explore vast search spaces while efficiently managing computational resource costs. Additionally, the framework facilitates a seamless self-revision process, allowing LLMs to iteratively refine and improve their outputs without extensive prompt engineering. Through various experiments, the authors illustrate ThoughtSculpt's potential across diverse tasks, highlighting its versatility and broad applicability. The results underscore ThoughtSculpt's capacity to enhance LLM performance in challenges requiring continuous thought iteration, such as open-ended generation, multi-step reasoning, and creative ideation. In this study, all datasets used in the experiments have been sourced and cited appropriately, ensuring academic integrity. The experiments primarily use GPT 3.5 and GPT 4, which are advanced language models capable of generating human-like text. However, these models raise ethical concerns regarding potential misuse, such as spreading misinformation or generating harmful content. It is crucial to implement robust mechanisms to prevent such misuse. ThoughtSculpt aims to enhance the reasoning capabilities of language models but does not include inherent safeguards against generating harmful content. Therefore, users are strongly advised to exercise caution and implement effective safeguards to mitigate risks. In the experiments conducted, the authors prioritize transparency and reproducibility by using publicly accessible datasets. For the content evaluator and the story outline improvement task, they employed FLAN T5, an open-source model, to further facilitate reproducibility. Additionally, the authors plan to make their code base available for reference and validation upon publication. However, they acknowledge that the use of GPT 3.5 and GPT 4 through the OpenAI API may affect reproducibility due to potential changes in the API by OpenAI. Thank you for watching.